Hello guys, welcome to another session on Zero Trust Networks. In this session, we'll be looking at how to realize a Zero Trust network. For better understanding of this video, I would definitely recommend you to watch the previous videos in the playlist. Let's get started. This session will help to develop a strategy for taking the knowledge in the previous sessions and applying it to their system. Zero Trust networks are very likely to be built around existing systems. So in this session, we'll focus on how to make that transition successfully. It is important to remember that Zero Trust is not a product that can be bolted onto the network. It is a set of architectural principles which are applied based on the needs and the constraints of the network. This session is not a checklist of changes to be made, but rather a framework for how to approach realizing in a Zero Trust network in your own system. Before setting out to build a Zero Trust network, it is important to choose the proper scope for the effort. All networks must be authenticated before being processed. In a Zero Trust networks, all the packets received by the system are immediately suspicious. As such, they must be rigorously inspected before allowing the data within them to be processed. Strong authentication is the primary mechanism by which we can accomplish this. Authentication is absolutely required in order to gain confidence about the provenance of network data. It is the single most important component of a Zero Trust network. Without it, we have nothing and are forced to place trust in the network. All the network flows should be encrypted before getting transmitted. The physical accessibility of a network link to unsafe actors makes it trivial for the network to be compromised. Moreover, in a physically secure network, bad actors can digitally infiltrate a system and passively probe the network for valuable data. By encrypting data on the device before transmitting on the network, we reduce the attack surface of that communication to the trustworthiness of the device itself, namely the application and physical device security. Authentication and encryption must be performed by the endpoints in the network. Since Zero Trust networks recognize the threat that trusting network links pose to the security of a system, it is important that the secure communications be established between the application layer endpoints. Adding middleware components that handle these responsibilities can leave the upstream network communications exposed to physical and virtual threats. As a result, a system that claims to be Zero Trust is required to implement encryption. All network flows must be enumerated so that access can be enforced by the system. Zero Trust networks depend on data that defines the expected characteristics of a network. Therefore, defining every network flow is critical to safeguarding the network. A simple process for defining expected flows brings enormous value in terms of network enforcement and change auditing. The list of expected network flows is needed, without which a Zero Trust systems are unable to highlight unexpected communications which need attention from either administrators or it should be denied. The strongest authentication and encryption suite should be used within the network. Zero Trust networks assume a hostile network environment, so strong authentication and encryption suites are an important component in the security of a Zero Trust network. One should refer to security standards like the NIST encryption guidelines to pick strong cipher suites. System administrators should always aim for the strongest suites possible, but the device and the application capabilities might limit the types of suites that are available. In these cases, administrators should be aware that by reducing the strength of these suites, security is being compromised in the network. Authentication should not rely on public PKI providers. Private PKI systems should be used instead. Using a public CA also presents another threat. State actors have become more aggressive in using judicial powers to force organizations to act against the trust guarantees that they provide to their customers. Given this aggressive stance, allowing state actors into trust mechanisms of a Zero Trust network should be given a pause. Based on these concerns, Zero Trust networks should prefer privately held PKI systems. Endpoints should be configured to allow certificates signed only by the private PKI system. Devices should be regularly scanned, patched, and rotated. Devices should be regularly scanned to capture the software that is running or installed on the device at a given point in time. Scanning can be used to discover and prevent known malicious softwares from running on the device, but the administrator should assume that the malware prevention software, like antivirus software, will always be imperfect. Keeping devices fresh is also very important. System administrators should have a plan for regularly installing the latest security patches. Additionally, a regular device rotation policy will help ensure that devices don't accrue craft, which can compromise the security of the system. Building a system diagram is an important first step towards realizing a zero trust network. Having a clear picture of how both internal and external communication is occurring will be used when designing system communication channels. A diagram like this is a good starting point for building a zero trust network. Directionality is pretty much important in this. System diagrams are often maligned for being horribly out of date. These diagrams are typically built by hand, which requires a large amount of human effort. So, if these systems are useful but often out of date, the natural question is how much time and effort should be put into their creation? A good path forward for an existing network is to first observe the communication that is flowing through the network. You can capture this communication using tools that log flows. Once the flow information is captured, producing a system diagram will be an exercise in categorizing classes of communication. A network flow is a time-bound communication between a source system and a destination. A single flow could be directly mapped to an entire conversation when using a bidirectional transport protocol like TCP. For unidirectional transport protocols like UDP, a single flow might only capture half of a network conversation. This is because while two UDP flows might be logically related, an observer on the network may be unable to make that association without a deep understanding of the application data. Capturing all the flow activity in an existing production network is a logical first step for a system that wants to move to a zero trust model. Logging flows in a network over a long period of time is a non-invasive way to discover what network connections exist and should be considered in the new security model. For a very large network, capturing and categorizing all network flows could be an enormous undertaking. The natural question is whether capturing all network connections is a requirement for transitioning into a zero trust network. Fortunately, a zero trust network can be incrementally realized within an existing perimeter based system. One can leverage the existing perimeter or network boundaries to build a zero trust network on either side of the boundary. The zero trust network model can then spread from zone to zone, enhancing network security of the existing system while maintaining the operational security measures already in place. A fully matured zero trust network will have at its core several control plane systems which provide critical security services. While having these systems is ideal, it is possible to iterate toward the idealized deployment while using common infrastructure systems initially. The components, however, are cheating with configuration management. The results and logs of the configuration management is fed back into the loop of the configuration management to effectively design policies. Application authentication and authorization. Authenticating load balancers and proxies. A relationship oriented policy designed for the zero trust network. How effectively and securely a policy is distributed. I'm not getting into each of these services in detail as we have already seen in the previous sessions. Security policies need to be captured in a format that's separate from the individual devices that are used to implement these policies. Having policy captured separately allows for auditing of the implementation against a desired policy. The policy definitions can be reused when switching underlying enforcement systems. A simple approach to safely introducing policy changes can be achieved using the rollout procedure. First, take a subset of the desired policy, which we will call the proposed policy. Deploy the proposed policy in a logging only fashion. Collect the production traffic over a sufficient period of time. Investigate the traffic which would be rejected should the proposed policy be enforced. Enforce the proposed policy. Repeat this process until all the desired policy has been deployed. When all the desired policy is in place, enable a policy which rejects traffic by default. Zero Trust proxies are application level proxy servers which can be used to secure a Zero Trust network. Proxies are deployed as infrastructure to handle authentication, authorization, and encryption responsibilities. Zero Trust proxies can operate in two different modes, reverse proxy or forward proxy. In a forward proxy mode, a non-zero trust aware component needs to make a network request to another zero trust system on the network. Since the non-zero trust aware component is unable to work with the control plane to initiate the request properly, it communicates through the authentication proxy to handle that responsibility. In reverse proxy mode, the proxy is receiving connection requests from zero trust enabled clients. The proxy receives the initial connection, validates that the connection should be allowed, and then passes the request to the application for processing. Since the exact architecture of a zero trust network is dependent on the details of a particular organization's network, it can be hard to see how all the pieces fit together. To help visualize how these principles manifest themselves in different situations, we are going to explore the experiences of a couple of organizations that have successfully transitioned to a zero trust model. Google's BeyondCorp effort focused on bringing zero trust network architecture to the client server interactions that their highly distributed and mobile workforces use every day. PagerDuty's cloud agnostic network focuses on server to server and cross cloud interactions which needed to be secured from both external and internal threats.
The first case study we're going to look at is Google's BeyondCorp on how it is implemented Zero Trust Network. If you look at the following figure, you will see BeyondCorp consists of many cooperating components to ensure that only appropriately authenticated devices and users are authorized to access the requisite enterprise applications. BeyondCorp securely identifies and tracks all the managed devices using a master device inventory database and device certificates. BeyondCorp uses the concept of a managed device, which is a device that is procured and actively managed by the enterprise. Only managed devices can access corporate applications. A device tracking and procurement process revolving around the device inventory database is one cornerstone of this model. As a device progresses through its life cycle, Google keeps track of changes made to the device. The information is monitored, analyzed, and made available to other parts of BeyondCorp. Because Google has multiple inventory databases, they use a meta inventory database to amalgamate and normalize device information from these multiple sources and to make the information available to downstream components of BeyondCorp. With this meta inventory in place, they have knowledge of all the devices that need access to the enterprise. All managed devices need to be uniquely identified in a way that references the record in the inventory database. One way to accomplish this unique identification is to use a device certificate that is specific to each device. To receive a certificate, a device must be both present and correct in the device inventory database. We store the certificate on a hardware or a software trusted platform module or a qualified cert store. A device qualification process then validates the effectiveness of the certificate store, and only a device deemed sufficiently secure can be classed as a managed device. These checks are also enforced as certificates and are renewed periodically. While the certificate uniquely identifies the device, it does not single-handedly grant access privileges. Instead, it is used as a key to a set of information regarding the device. BeyondCorp also tracks all the users in a user database and a group database. This database system tightly integrates with Google's HR process that manages job categorization, usernames, and group membership for all the users. An externalized single sign-on system is a centralized user authentication portal that validates the primary and second factor credentials for users requesting access to the enterprise resources. After validating against the user database and the group database, the SSO system generates a short-lived token that can be used as part of the authorization process for specific resources. All enterprise applications at Google are exposed to external and internal clients. This is done via internet-facing access proxy that enforces encryption between the client and the applications. The access proxy is configured for each application and provides common features such as global reachability, load balancing, access control checks, application health checks, and denial of service protection. This proxy delegates requests as appropriate to the backend application after the access control checks. In a nutshell, this is how Google's BeyondCorp implemented its zero trust network. There are a lot more details than this, but this is beyond the scope of this session. Let's look at PagerDuty's cloud agnostic network. PagerDuty is a platform that organizations use to power their incident response. Users are able to integrate their existing tools like monitoring, ticketing, and reporting systems using PagerDuty's API. Given the critical nature of the service being provided, a zero trust network was ideal to meet both the reliability and the data privacy requirements of the system. PagerDuty's zero trust network primarily deals with server to server interactions, purely within a multi provider public cloud environment. The key asset used to construct PagerDuty's zero trust network is its configuration management tool called Chef. Chef was already being used to configure every virtual machine in the system, so it is a readily available automation layer which could be leveraged to build a zero trust network. With the configuration management, policy could be centrally managed in code while distributing the enforcement into the entire fleet. This approach had a number of benefits. The network compute power scales as the number of instances increases, removes the need to buy our large shared hardware as the network grows. Failures tend to be more isolated. Instead of having the firewall, the system ends up having many smaller firewalls. A failure of a single firewall affects a much smaller set of traffic and oftentimes can be routed around. Another concept PagerDuty used is to create dynamically calculated local firewalls. Without a consistent provider supplied firewall solution, PagerDuty found it needed to ensure that each host was secured without relying on provider systems. To meet that need, Chef was taught how to generate IP tables configuration based on its existing knowledge of the system. This created dynamically calculated local firewalls. If the flow does not match the whitelisted rules, its packets are dropped. For network encryption and authentication, PagerDuty decided to implement an IPsec host-to-host mesh network. This network architecture has a number of benefits. All packets are encrypted and authenticated by every node in the system. Since encryption and authentication is distributed throughout the system, as the number of hosts grew, the capacity to provide the critical function grew as well. PagerDuty's user access control is deployed in a centralized fashion, much like the networking systems previously discussed. Instead of relying on a decentralized LDAP system, local users and groups are programmatically constructed on each host in the network. This approach removed the dependency on the network, which helped the systems continue to operate even during challenging periods. PagerDuty's network, like most networks, is an ever evolving system. The network transitioned from a traditional design to a zero trust network over time while production traffic was flowing. How they have achieved it? They've defined new policies, and these policies are deployed in a manner that did not affect the production system but instead used to collect logs and metrics. And these metrics are inspected over a long period of time to ensure that the behavior is desired. And the policy is slowly enabled across the fleet, growing from a small percentage to 100% coverage. This simple procedure could be used to reduce the risk of most production changes. It is much better than the common approach of using a scheduled maintenance window. The slow rollout pattern is used to deploy most changes in PagerDuty systems. That brings an end to the cloud agnostic network by PagerDuty. In the next session, we will be looking at the adversarial view of zero trust networks. We'll start with identity theft, then go on to social engineering, and then look at how to avoid DDoS, how to prevent endpoint enumeration while designing a zero trust network, and the importance of untrusted compute platforms, ways of physical coercion to get the authentication or authorization credentials, and finally the invalidation. Thank you for watching the video. Bye bye.